Hello everyone, and welcome back to another video from the lecture series for the course of database design and implementation. Okay. This is part 2 of or continuation of the topic for relational data models. Okay. So to quickly recap the contents of the previous lecture, what we had done. So a quick recap of part 1. We had talked about the properties of a relational table, and then we learned about the mathematical concepts or the concept of determination that helps us, or from which we developed or understood the concept of functional dependency and full functional dependency. And using these two math concepts, we learned about the concept of database keys, wherein we learned different keys like super keys, candidate keys, primary keys, and then separately we learned about foreign keys and then secondary keys. And thereafter we discussed about the integrity rules that must be enforced within the database environment in the form of the entity integrity rule, okay, and then the referential integrity rule, which is basically what properties of the primary key and the foreign key must be followed when trying to implement these two integrity rules. Okay. So the agenda for part 2 of this particular chapter or the relational data model is we are going to be talking about the different relational operators that we have within the relational model, right? Mostly about the theory of it, such that it will act as a foundation when we move towards SQL later on, 3 or 4 chapters later, okay, or about a month later. Then we will talk about implementing the relationships or the relationship types using keys. And then finally, we will learn about some notes or some remarks, or let's say revisiting data redundancy, the concept of data redundancy. Now that we have a bit more idea about what keys are and stuff like that. And then brief discussions of data dictionary and database indexes. Okay. So these are the topics that we will be discussing for this particular lecture. Okay. So let's take the first topic, which are relational operators within the database environment. So relational operators can be categorized in two ways. The first category of relational operators are unary operators, whereas the second category of relational operators is known as are the binary operators. Okay. So basically unary operators are those operators which have a single operand, and binary operators require two or more operands. Okay, or basically two operands if you collectively do it. So under the unary operators, we have what is known as the select and the project operators. Okay, so select is mathematically represented using a sigma, and then project is mathematically represented using a pi. Right? Thereafter, in the binary operators, you have many different types of operations, right? And those operations can range from performing what is known as union, intersect, difference, product, divide, and then finally the join operation. Okay. So the union is represented by this capital U. Intersect, difference is basically difference. Product is represented by the cross symbol because it is the Cartesian cross product. Divide, and then join operation can have many different symbols because there are different types of join that you can perform. But typically, it is represented using the bow tie symbol. Okay, so if you're looking for, this is known as the bow tie. Then there are different forms of join. One is known as the inner join operation. Okay, and the other one is known as the outer join. Okay, in the inner join, again, you have many different types of join operation, which is the natural join, equijoin, and then theta join. So the natural join is represented by, of course, the bow tie. The equijoin is represented like this, and then the theta join is represented like this, where the value of theta can be greater than, less than, greater than equals to, and then less than equals to, right? Whereas outer join, there are two types of outer join. One is known as the left outer join. Okay, I'm simply just going to write left, but it is outer join, remember that. And then the right outer join. You can also have, if you combine left and right together, you can get what is known as the full outer join as well. But we necessarily don't go there. So the left outer join is represented like this. Okay, you open the left part. The right outer join is represented similar to that of the left outer join, but you open the right part. And as you have already guessed it, the full outer join, you open both the left and the right sides. Okay. So these are essentially, and in addition to that, sometimes the Cartesian cross product, when you're implementing, is also known as the cross join. But necessarily, it is not a join operation as such. But there is a reason why it falls within that category, because when we learn a bit more about the inner join, we will see that join is not a fundamental relational operator. And as a result of that, you need these other fundamental relational operators in order to construct the operation of a join. Okay? And one of those operations is the product operation. So that is why sometimes when you're implementing, when you're using the actual SQL syntax, you will be mostly referring to product, the Cartesian cross product, as cross join. Okay? That is the idea behind it. So what we will do now is we will go through the slides one by one and talk about the concept of these different relational operators. Okay. So the first one is the select operation. Okay, so let's say 1. The select, sometimes it is also known as restrict, okay, operator, also represented as sigma. So the input to the select operator is basically the table. Okay, so the input is basically one table. Okay, so one table is kind of to a certain degree it's a bit misleading, because you can apply, later on you will see that you can apply a binary operator to combine the rows or columns, rows and columns or columns of different tables and create a new table. But at the end of the day, it does apply, because whatever you're passing it is in the form of a single relational table, right? And this is going to give as output a single row, a row. So let's just one or more rows as output. That satisfies the output condition. Okay. So of course, the reason why I wrote that satisfies the output condition within the brackets is because you may or may not specify a condition. You don't necessarily have to specify a condition. So let's say, as an example, you want to output students having GPA greater than or equals to 3.00. So this is what you want to output, right? So if you want to express this using the relational operator in the relational algebra form, then we would like the relational notation of the select operator followed by the input, which is going to be the table. So that is going to be the name of the table. So our name of the table is student. And then we have a restriction or a condition here. So that is written as a subscript to the relational operator. So we will have to write in the subscript student GPA greater than or equals to 3.0. Okay. So now in addition to this, if we add one more criteria, that student GPA greater than 3.0, and so let's say example 2. So output students with GPA greater than equals to 3.0 belonging to the CSE department. Okay. So then this will be represented as sigma student GPA greater than 3.0 and the logical and, because both of these conditions needs to be true. Student department equals CSE, assuming that this is the data type that we have chosen in order to encode the department that the student belongs to, and followed by the input, which is the name of the table, students. Okay, so this is going to return all the rows from the table student and all their attributes, where student GPA is greater than 3.0 and student department is CSE. So in addition to and, you can also combine multiple conditions by using the remaining logical operators, such as logical and or not, to combine multiple conditions. Okay, so this is the reason when we began this particular chapter, we said that it is kind of intuitive as long as you understand logic formulation. Okay, because we understand the concept of what this operator does now, but it depends on us to understand how logic needs to be formulated in a programming fashion to be able to express this in the relational algebra format. Otherwise, it's going to be really difficult. Okay. So now let's say this is the case. This is what we have in this particular example. But now in this example, I don't want to output all of my rows, because if you remember, the student table had many attributes, right? So I don't want to output all of the attributes. I simply want to output the names of the student and their GPA and the specific value of the GPA. So in order to output specific attributes from a given table, okay, we use what is known as the project operator. Which is represented by using the notation pi. Okay. So again, it is a unary operator, so the input is one table, and the output are specific rows, with only the specified attributes. So that means, as an example, if we want to output only the student name and their GPA from the student table. So if this is our goal and we want to express this in the relational algebra format, then what we will be doing is we will be taking the aid of the project operator, and then we will be specifying student name, comma, student GPA from the table student. So this is pretty straightforward way, right? So if we read between the lines, the project operator helps us with vertically partitioning the table, okay? Whereas the select operator helps us to horizontally partition the table, okay? Which is because it's going to selectively chop off some of the rows that does not meet the select criteria, and this is only going to project the attributes that we have specified in the project subscript, okay? So now we can combine select and project together to both vertically and horizontally partition our table, and this is known as the property of closure. That is, you can combine multiple relational operators together in order to get a particular output. So that means if our example, if we want to output student name and GPA for only those students with GPA greater than equals to 3.0 and belonging to the CSE department from the student table. Okay, so if you want to do this, then first we will have to apply our conditions in order to select the rows from the table that satisfies that condition, right? So then we will be writing sigma student GPA greater than equals to 3.00 and student department equals or equality CSE, okay, from the student table. So this will restrict or horizontally partition the student table and select only those rows which satisfies this condition. Now on top of this, we can apply our project operation and say that from this temporary result, only output the student name, comma, student GPA, and disregard the remaining attributes that are there. So the output, the overall output of this table can be stored in what is known as a relational variable, and we can call that A. So relational variable are basically those variables that helps us store the values returned by relational operators or relational tables, right? So just like you have a variable, and if you are performing, let's say, an operation like C equals to B plus A, where B, A, and C are simple variables. So C is the label of the location where the value will be stored, and within the location, you have the actual value. So now, instead of simple variables, what relational variables will have is basically the label will be the name of the table or whatever it is that you want to give it as a name. And then the content will be basically a relational table that is generated from a relational operation. Okay, so that is what relational variable simply means. Okay, so now one question is, before we move forward, a question that can come up in our mind is why learn? relational operator / relational algebra notations. So these are just theory, right? So why learn about this? Well, the reason is there is a direct projection from the logic formulation of data transformation techniques using relational algebra into SQL. Because if you learn the foundations of relational algebra and relational operators and how to formulate your logic using these operators, then when you arrive at SQL, learning structured query language, all that will remain is to basically find the corresponding syntax that will help you do certain operations. So for example, this previous example that we were talking about, where we had, and a quick note before we move forward, always read any relational algebra expression from right to left. Okay, so that means the student table, select from the student table the rows which satisfies these conditions, and then project the attributes of student name and GPA, not from left to right. It's always from right to left. It's the precedence of operators, if you remember from your programming classes, that it always goes from right to left necessarily. Okay. So now, again, coming back to our original discussion, if we had this example here where we had project student name comma student GPA, after selecting the rows where student GPA is greater than equals to 3.00 and student department is equivalent to CSE from the student table. So if you can formulate this sort of logic, right, and always remember, read it from right to left in this formulation. Okay. So if you're able to formulate this logic, then when you come to SQL, the SQL portion of this, you will basically realize that this has a direct correlation to how you write your SQL queries. Okay. So SQL queries, the typical SQL queries of select from where that you see, is not the same as that of the select of relational operators. So please don't confuse that. So let's choose a better ink. I want to have some effect. So when you formulate the logic, you first do from student. And that is where the correlation is. You first specify the input, right? And then the criterias. So you will have the criteria written in the where clause. So where student GPA is greater than 3.00 and student name, or what is it, student department, is equivalent to CSE. Okay. And then select student name, comma, student GPA. Okay. So this is basically the SQL syntax. So when you read the SQL syntax, you might think that, oh, first select, then from here, where the condition is this. But under the hood, when the implementation is done, that is not how the order of operation happens, right? And that is why you need to be able to abridge the gap from the relational algebra theoretical logic to the SQL syntax to have a better grasp and a stronger foundation when you're working with data transformation related to database implementation. Okay, so knowing this will make your life easier here when you're going to this particular domain. So then you're not trying to memorize the queries, but you can formulate it by knowing what the relational algebra counterpart was actually supposed to be. So then all that will remain is to know which syntax in SQL, so these three are the syntax, helps you do what you have expressed in relational algebra. And that is very powerful because now you're not just, in a very blind fashion formulating your SQL queries by memorizing what the syntax do, but now you actually understand how the syntax came to be and how the order of execution is happening by actually knowing the theoretical or the conceptual foundations of the relational operators. Okay, and that is very, very useful. Okay. So now going forward, we have our binary operators. So the first binary operators that we have is union. Okay, and it is represented by the big U or the big cup. I think that is what the latex formulation is actually. So that is what we have. Now, again, we will be growing through some theoretical concepts and some simple examples, right? So if you want more examples, I would strongly recommend that you read your book, which has like proper tables listed, and or even the formal slides that I upload. You can look at the examples from there. But here, as far as the notes are concerned, the examples might be a bit in a draft fashion, right? So I won't be writing entire tables and trying to visualize that. So let's go with that. Okay. So now, union. To perform union, there are some prerequisites. So the first prerequisite is that tables must be union compatible. So what this means is that they should have that is, they meaning the tables, should have the same number of attributes with similar data types and attribute domain. Okay. So if this is not satisfied, then you cannot apply union and then many other operators on those two tables. Okay. So the input, now that you have assured it, input is going to be two or more union compatible tables. Okay. And the output is basically going to be a combined table excluding duplicate rows. Okay. So that means, and I'm taking this example from the book. Okay. So let's just go to the formal slides and then take the example from the book that we have in order to better understand this. Okay. So here, let's say we have two tables. Okay. So we have one table, which is the supplier, this one here, which has a set of product descriptions, the product code, and then the product file or the product price. Okay. And then you have another table, vendor, which consists of similar attributes with similar data types and similar attribute domain, which has the same set of codes. So now, since you have two different tables expressing the same set of information, then you might want to combine them together into a single table for whatever analysis purposes, right? So then what you can do is you can use the union operator by expressing it in this relational algebra format. which will yield a final table that combines the rows of these two tables together. But then it excludes the duplicate rows. So you have to keep in mind. Okay. So in this particular example here, we have 1, 2, 3, 4, 5, 6 rows. Okay. And here we have 1 and 2 rows. So there is no repetition of microwave and dishwasher in this particular table, right? So as a result of that, this original table or this table here gets appended onto the first operand, okay, resulting in this final. So you have the information, the 6 rows from the first operator and then the 2 rows from the remaining operator. But however, if there was an instance where this product code, let's say dishwasher, was repeated here, then it will not show up twice. That row will not show up twice in this particular table. Okay, so that means, so that is what union does in a pretty simple fashion. So the next one, so again to recap, if you have a relational table, let's say n, no, not n, let's say you have a relational table RT1, and if you union that with a relational table RT2, then it will append the rows together to create a new table, let's say RT new. Okay, so remember, rows will be appended. Okay, so first all the rows of RT1 table, relational table 1, and then all the rows of relational table 2, excluding the duplicate rows. Okay, so if there is anything duplicate, it will only appear once and not twice. So that is basically the difference. So the next one is basically the intersect operator. Symbol is this. Input is again going to be the same, 2 or more, union compatible, so here I think we should just put the output is a combined table excluding the duplicate rows. Okay, here 2 or more union compatible relational tables, and the output is going to be the common rows of the two or more tables. Okay, common rows. So that means if you look at the example again, keep. So the example is, let's say if you have a student and then you have an employee table. So there are chances at times when a grad student also acts as an employee, right? If they are, let's say, a TA, or if you yourself, not just a grad student, but if an undergrad student is working, let's say, in the library and other places that is under the university, right? So that means their information will appear both in the student table as well as in the employee table. So if you union them, you will basically find the rows which are existent across both the tables, 2 or more, right? So here in this example, we can see that this student, Franklin Johnson, right, appears both in the student table as well as in the employee table. So when intersect is applied, and it can only be applied because both of these tables are union compatible, right? Because they have 2 attributes. The data types of both of these attributes match, and their attribute domain must also match, right? So when that happens, basically the output is another relational table consisting of the common rows. Okay. So thereafter, we have the difference notation. So the different notation is kind of funny. So for example, see book or slides or formal slides. Okay. So then for the next one, oh, this is going to take a lot more slides than this. Let's just see if we can end at 45. Okay, so where were we? Here. So the next one is difference, okay, which is basically a subtraction notation. So again, the input is going to be 2 or more union compatible relational tables, and the output is going to be rows which are present in the first table but not in the second one. So that means, and remember, difference is not commutative. So what this means is that if you have two tables, A minus B is not the same as B minus A. Okay. So for example, again, if we take the example from intersect, where we were trying to find students who are also employee. So instead of students who are also employee, if you want to find students who are uniquely students, uniquely is not the best word, but who are not employed by the university, then you can simply do students minus employee. So this will give you only the set of rows which are specifically student and not employees. Okay, so let's look at the example that is there in the book, and if we have something else. Okay, we don't. Okay, it's the same example. I think I just projected it without knowing it myself. Okay, so the next one is product, the relational operator of product. So let's save this. One thing I realized in doing all of this is that when you're using ink for PowerPoint, apparently it increases the size of PowerPoint many folds. That is something I was not aware of. So the next one is basically the product, the Cartesian cross product. So the input is basically two relational tables and the output is a complete pairing of rows from one table with another. So that means, let's say if we have student table, okay, which has the names of all the students, and then if we have a courses table, which has names of all the offered courses. Let's say it is CSI 3450 CSI 3610, CSI 2300, and so on, right? And then you have students, let's say ABC, DEF, PQR, XYZ. So if you do student cross-product courses, then the output is basically going to be ABC CSI 3450, ABC CSI 3610, ABC CSI 2300, then DEF CSI 3450, and so on, right? So that means each row, a complete pairing of the rows from one table with another. So ABC will be paired with all three of these to create the first three rows. Then the next three rows will be DEF paired with all of the other. Same goes for PQR, and then same goes for XYZ. So as a result of this, if this table had 4 rows and this table has 3 rows, then the output table will have 4 cross 3, 12 rows. But again, remember that product is not commutative either. So that means if you do A cross B, is not going to give you the same result as B cross A, because it is a Cartesian cross product and not a straightforward product, right? So the overall output, if you do courses product student, will still be 12 rows, right? However, the nature of the rows will be different. You will have CSI 3450 and ABC as the first row, then DEF, PQR, XYZ, and then you will have CSI 3610, so on and so forth. Okay. So if we take the example now, here, so you have, in this particular example, you have the product description and you're trying to create a pairing with the different types of aisles or store aisles where you can store those products, right? So if you do that, so the net total is 6 cross 3, 18 rows, and then you have a pairing of the first product with all the 3 rows of the second table, and then the second product with all the 3 rows, and so on and so forth. Okay, so that is basically product. So the next one is a bit fun, or it is basically the most important relational operator that you can have. So instead of going back and forth between this nodes and this table, I'm just going to say from join onwards, see examples in formal slides. Okay, and notes will be notes for only very important remarks. Okay, because this is just overdoing it and taking more time than it should. Okay, so coming to our next one, we have the join operation. So join operation is not a fundamental relational operators. That is, it requires the aid of other relational operators, basic or primitive relational operators, in order to form join. So as we discussed at the beginning, there are different types of join. Okay, so natural join and theta or equijoin is basically a part of inner join. And then you have outer join, which has 2 types, left outer join, right outer join, and if you combine them, you can get the full outer join. Okay. So what join essentially is that when you're looking at union, intersect, and all these different types, differences, at the end of the day, it is taking the input of 2 relational tables and it is combining the results given the nature of the concept of its operator, and then it's yielding an output, right? So taking that concept further, join gives us another intelligent way to be able to perform that combination of those two tables. So to motivate that example, let us say we have this table, customer, which has the customer information in the form of the customer code, last name, zip, and agent code, where agent code is the foreign key, because agent code is the primary key of the table agent. An agent table basically has the information of agent code and then agent phone number. And the primary key of this table is basically customer code, right? So now, if our motivation, not motivation, but if our goal is to basically find the customers who have been assigned to an agent, right? So that is what we are trying to do. So the query that we are trying to solve here is output the customer who has or who have customers who have an agent assigned, okay? An agent assigned to them. This is what we want to find out, okay? So if you want to do this, then what will end up happening is it is much easier if you perform join on these two tables. So now in order to perform join, the one that we will discuss here is basically natural join. When we write, let's say table A, natural join table B, or even when in SQL we are going to be implementing this operation, from a high-level perspective, it may seem that it's just like any other relational operators because you don't have to do anything specific, right? However, under the hood, when it is being implemented, there are three specific SQL operations or relational algebra operations that are being performed in order for the output of the join operation to be yielded, so that we can yield the output, right? So the first step is basically we perform the product of the two tables. And then after that, based on what is known as the join criteria, we perform the select operation. So for now, that join criteria is the equality of the common attributes across the different tables, okay? And then finally, the project operation is performed in order to eliminate the duplicate attribute that is present due to the combination of the two tables, okay? So what the final output gives us is basically a table which includes the matched pairs, and this keyword is pretty important. So whenever you're trying to express what join does, you have to say that it gives an output of the matched pair of rows from the input tables. This keyword expression is pretty important. You have to remember this, okay? Okay, because when you are asked, there will be a typical question that what is the difference between an inner join and an outer join? And if you remember this keyword, it will be much easier to express or explain yourself compared to not remembering this keyword and then going through this entire history of explaining what join does and how it differs in inner and outer join, okay? So you have to remember inner join, which is a composition of natural join, equijoin, and theta join, returns the set of matched pair of rows from the input tables, okay? So now let's understand this or expand these three inner operations that are being performed in order to facilitate join. So this was our table, and the first operation that we are saying is we have to perform the product of the two tables. So as we learned from product, if you perform the product, the Cartesian cross product, then it will simply create the pairings. So that means this first row here will be paired with the 4 rows here, and then the next row, and then the next row, in order to generate the final product table or the intermediary output. So here we have Walker being paired up with all the agents. So now as you can see here, Since this column here, the agent code, was present in the customer table, and the agent code was also present in the agent table, this is where this equality of the common attributes is coming from. Because now we have those two tables which have the same set of attributes, which has been generated in the temporary table after performing the Cartesian cross product, which is in this format, right? So we have both this particular attribute and this particular attribute being the same. So we want to find the equality, and we want to select the rows which matches the values from these two attributes, the equal attributes, right? So that is going to be the second step, is from the common attributes, which is agent code from the customer table and then agent code from the agent table, we are going to select the rows where the data values are common. So 231 is not equivalent to 125, but 231 and 231 matches. So we are going to select this row for the next temporary output. Similarly, it will go through the entirety of the table, and here we can see that we have 1, 2, 3, 4, 5. 5 rows that are matched. So this is going to be the next temporary output, and all the other rows where the equal attributes do not match in values are discarded. So that is the second step. And thereafter, so this is going to be the final output of the select operation. So now, as you can notice, that once the other rows where the values were not common were discarded, and this is what remains, you can see that there are two attributes which are basically duplicate, right? Because they are referring to the same thing, same context. So we don't need them to appear in the final output. So as a result of that, we do the third operation, which is the project operation, where we simply eliminate the duplicate attribute and make it appear once. So if you remember the logic of project, we can selectively choose which attribute should come in the output. So this is the output. So if you simply perform join operations, right? So if you simply perform join operation, if you simply write customer join agent and you get this output, this is what is happening internally. It first performed a product, then applied the select on the common attributes, and then it performed a project in order to remove the duplicate rows. So now, Equijoin, how it differs from natural join, is the fact that even though both operates with respect to equality, Equijoin, if you perform, does not apply the final project operation in order to remove the duplicate rows. Okay, so that is typically the difference. And then thereafter, the equality condition is also needs to be explicitly specified. Okay, in natural join, you might have this question that what if there are no attributes which are common across those two tables which you perform on which you're trying to perform the join? Well, your output is going to be null in that criteria, right? However, here you can specify that if the data type matches but the name of the columns don't match, you can still perform equijoin on top of that as long as they satisfy the data type, and you can perform the equality. Okay, so that is where equijoin differs from natural join. And theta join is basically giving us the capability to perform all operations which are not equality. So if we want to do, let's say, greater than, less than, greater than equals to, or less than equals to, then we can simply use the theta join, okay, for all other comparison operators. So that is what the join operation does. So inner join, keep in mind again this keyword, inner join is going to return only the matched records from the table, okay, or the set of rows which are matching. Whereas outer join, of course, it's not the opposite of inner join, but what outer join necessarily does is it returns the set of matched and unmatched records. Remember, records is another way of saying rows. Okay, so that is what outer join is. It does inner join, but on top of that, it also returns the ones or the rows which does not have any kind of matching with the other table. So that means if you do a left outer join, it's going to return you the result of the inner join plus rows from left table which does not have any pairing. Okay, whereas right outer join will give again the inner join plus rows from the right table that does not have any pairing. The rest are similar. Okay, so that means if you do left and right outer join, then you will have inner join, then the rows from the left table that does not have any pairing, and then the rows from the right table that does not have any pairing. Okay, so that is basically the difference between inner and outer join. And again, similar to inner join, outer join is also a non-fundamental relational operator. So as a result of that, in order to return the value of, or in order to return the output of inner join, it has to perform all the operations of join. So that means it has to do first product, select, and then project. Okay, and thereafter, in order to produce the set of unmatched records, it has to do difference from the original table in order to find which rows are missing, and then combine them and then join them together. Okay, so if we look at this example of left outer join, right? So here we can see in the first 5 rows, we have the result of our join operations. So this is the result of natural join. So that means these are customers who have been paired with an agent. But here, as you can see, since this is a left outer join, we said that in the left outer join, we will get inner join plus the rows from the left table, which doesn't have any pairing, right? So here, the left table was the customer table. So this last row is returning the customer who does not have any agent assigned to them yet. And as a result of that, this is basically null. Okay, so this is one example of left outer join. So thereafter, if you do right outer join, then you can find the agents who has not been assigned to any customer. So if you hired a new agent and you want to know if there are any agents who are available right now to manage a customer, then you can do it by using the right outer join in this particular setup. Okay. So now the important question is, why or when would you use the outer join? So if you look at the importance of outer join itself, left or right, then you can see that the first importance is basically if you're trying to migrate, let's say, a file system to a database environment, and you want to know if the referential integrity is preserved, then that is when you can apply any form of outer join, left or right, in order to figure that out, right? So the most important reason why outer join exists is to validate that referential integrity is preserved, that all the foreign keys are either referring to a valid primary key or they are null. Okay. And the other way, or the other smaller significance of outer join is to answer these kind of queries like, is there any agents that are currently available who are not managing any customers, such that you can distribute the workload in an equivalent fashion. Okay, so that is one of the smaller query significances for the outer joins, right? But other than that, the most important reason why you use outer join is to validate that when you're migrating a data set from, let's say, the file system domain to the database domain, then you can verify that whether or not referential integrity is preserved. Okay. So thereafter, we have the divide operation, which is to identify the output of one set of data if it is associated to all values of another data set. Okay. So divide always happens or takes place between a two-column table and a single column table, and in the single column table, that column has to be one of the two columns. So what we want to find here is, let's say if we have in this example, we have this two-column table where we have code and location. Okay. So what we want to find out is to which location this code A and B is related to. Okay. So A and B both are related to the location 5. So we can see that A is associated to 5 here and B is associated to 5 here. So the location that is related to all the values of this particular table is basically 5. So this is essentially important if you want to find out. In this particular case, it is pretty evident from the example that if you're doing inventory management and if you're trying to locate all the items, that is there any particular location where all these items are present or grouped together, right? So you can use the divide operator in order to be able to identify that, right? So other than that, let's say if we had added to ABC, let's say we had added D, okay, in addition to this. So then what would have been the output? So then we would have to find that is there any location which hosts A, B, and D altogether. So A is hosted in 5 and 9 and 4. B is hosted in 5, 3, and that's it. So there is one common. And then D is hosted in 7, 8. So there is no location that holds A, B, and D. So the output, if we have A, B, and D, is going to be null because there is no location. Okay. All right. So that is basically the divide operation. Okay. So this kind of sums up the different forms of relational operators that you can have in the relational model. Okay. So the next topic, just discard. So this topic of data dictionary and system catalog, where there is a problem of homonyms and synonyms, I would urge you all to do it as a self-study. Okay, it's not that big of a topic and there isn't much explanation there. So I'll just write here in our trusty notes slide. So we will say, just go back and not waste the space. So here we will say self-study, data dictionary, and system catalog. Okay, and the issues of homonyms and synonyms while naming tables and attributes. Okay. So after that, we have the next topic, the next important topic, which is implementation of relationships or relationship types using keys, using primary keys and foreign keys. Let's just make it more specific. Okay. So the first type, if you remember, the most common one that you can find is 1:m. So if we are implementing 1:m, okay, so what we do is, this is like a cheat sheet or kind of like a hack. Not the best way to express it, but for you to remember it, this is like easier. You take the primary key of the one side and embed it as a foreign key in the M side. Okay. So this is how you remember how you're going to implement 1:n relationships, 1:m relationships. So again, if you have professor and you have the primary key as, let's say, PID, which stands for professor ID, and then if it is in a 1:m relation, a mandatory 1:m relation with student, okay, and the relationship label is advices. Always remember, do not forget the relationship label. And the primary key of student is basically student ID, and the foreign key is professor ID. Okay, so this is how you implement professor and student. Thereafter, if you have 1:1, okay, and let's say you have professor and again you have the primary key as professor ID, and then you have a mandatory, let's say, not necessarily mandatory, it will be optional. Professor may or may not chair a department, but let's say you have the department here where you have the primary key as department ID, and this is 1:1, and the label is chairs. So the hack here is take the primary key of the subject and embed it as a foreign key in the object. So that means what we are trying to say here is, in a relationship, find which entity is the driving factor. Every relationship is a form of action to a certain degree, right? So find out which entity, when you're doing 1:1 specifically. If you read your textbook regarding the implementation, you will find 3 or 4 different criterias which are expressing different kind of conceptualized behaviors of how to find which primary key to embed where as a foreign key, right? But it all boils down to the fact that if you identify which is your driver entity, that which entity is driving the relationship, then you take the primary key of that entity and then you embed it as a foreign key in the other entity. So that means here I will take the driver because the professor is chairing the department. So the professor is subject and then the department is the object in this relationship. So the subject and object thing is coming from English. Okay, if you remember in English language statement, we had this grammar lesson where we were talking about subjects and objects, right? So that is where that is coming from, right? Or you can simply ask yourself which entity is the driver of the relationship, right? So here we will be embedding PID. However, if this nature changes, okay, so now if this state changes and this becomes, from here, we do department, employees, professors, okay. So now you see, given the nature of the relationship context, the driver changed. The driver of the relationship changed. Now, in this particular relationship, the driver is the department. And now, as a result of that, the professor becomes the object of the relationship, right? And the department becomes the subject. So, as a result of that, in that particular situation, you will take the primary key of the subject, which is department ID for this relationship, and you will place it in the object. So this way, you don't have to distinguish between what relationship type you're trying to implement, whether it is 1 is to m or 1 is to 1. We will come to m is to n, but that will also simplify itself later on, right? But I don't want to just tell you generically that it applies to everything, okay? But if it is just 1 is to m and 1 is to 1, which is the physical implementation, the direct physical implementations, yes, take the one side, put it in the m side, and then you have many more different guidelines or heuristics for 1 is to 1. I don't remember that from the top of my head. You can read it in your book, but what I will give you as an advice is just try to identify in a relationship which entity is the driver. You take the primary key of that entity, and then you embed it as a foreign key in the other entity, and then your job is done. Okay. So professor advises student, the driver is professor, that is professor is the subject of this relationship type, and then student is the object, so you take the primary key and then you embed as a primary key. And life becomes easier. But m is to n, you remember when we were introducing the relationship types in the data model, right? We said that this doesn't have a direct physical implementation, right? So now if you try to implement this with the same logic as that, or as directly as you did for your 1 is to m and 1 is to 1. And the example that we had was courses. Okay. So here, if we had an m is to n logical representation, then it was something like this. Okay. For now, we are expressing all relationships as mandatory. But once we move into the entity relationship model, you will see that not all relationship needs to be mandatory. Some of them, there could be optional participation. Okay, but we won't come there. So let's say this. So this has two relationships that is going from one direction to the other. Okay, so the one, but when you label it as m is to n, you can simply say student enrolls in courses. Okay, but when you are breaking it down into its smaller subparts, you can see here that a student can enroll in m courses. So now here, let's say if the primary key is student ID, okay, and then here the primary key is, let's say, CRS ID, okay. So now if student enrolls for courses, you might think that, okay, student is the driver of this particular relationship type. So I will embed the foreign key of student and place it here, right? So this will become student ID. But however, this is m is to n, and this is not 1 is to m. So if you just leave it at that, it would kind of mean that a given student can enroll in multiple courses. However, a given course can have only one student, which is completely untrue, right? So you also have a course can have multiple students. So that means from the bidirectionality of this particular logical relationship, from the other side around, from the other perspective, course is the driver. So that means here you will have to embed the course ID as a foreign key. So what will end up happening is, if you write it down for a given student in this particular table, right, you will have to specify all the courses that that student has taken. So implementation wise, when you write this down in terms of data entry, you will have student 001 registering for course ID or course ID, let's say 543. But if this particular student has registered for another course, let's say 541, then you will have to do 001 and then 541 and 001 663 and so on and so forth. Now note the fact here that this is your student ID and this is your course ID, but this is present in the student table. And the same situation will also happen in the course table as well. But what is noteworthy here is to pay attention to the fact that this was our primary key, and the primary key is no longer unique. And if the primary key is no longer unique, then it violates the entity integrity rule. Okay? And as a result of that, this kind of direct implementation of M is to N is not permissible. Okay? So in order to be able to implement M is to N, what we do is we translate M is to N when we want to implement, right? For implementing. So this is only for implementation purposes. Up until the logical representation purposes, there is no issue with M is to N. It is understandable. But when you're implementing it, you have to translate M is to N into two 1 is to M relationship with a linking table. Okay. So this is a manufactured table, or this is an artificial table that is implemented in the database environment only for the purpose of establishing the M is to N relationship between two entities. Okay. So now if we want to implement this, we have to create another table. Okay. So therefore, the relationship of student and course will now be broken down into something along these lines. So we will again have student. Okay. So you have the option to express this in your graphical design or not. Okay. But when you're going to be using the workbench, the moment you express two entities as M is to N, it is directly going to express it using the linking table. Okay. And the reason behind that is design can be directly translated into database implementation from workbench. So don't worry about that now. We will get there and we will address it in a steadfast fashion. Okay. So then we will have course, and let's say now I will go create and call it let's say registrar or registration, registrar info. Okay, something like this, whatever name you would like to give. So now this entity will have a 1 is to M relationship, and that relationship will be registers, okay, or enrolls. And this will have a 1 is to M, and let's say it has, okay, or something like this. If you can come up with a better label, that will be great. Okay, so student had the primary key of student ID, and then course had the primary key of course ID, and then registrar info, since it is in 1:n, student registers into the registrar info, right, into the registrar database. So again, for this relationship, this is the driver. So I'm going to simply add my new foreign key 1, which is going to be student ID, and then I'm going to add my other relationships foreign key, which is foreign key 2, as course ID. And now, in addition to this, you can add your own primary key and say, let's call it registrar ID. But you can also choose a composite attribute of the foreign keys to act as a primary key as well for this linking table. And this table is solely generated for the purpose of implementing the two MS or the MS to N relationship between two real entities. Okay. So now, in addition to this, of course, you can have other information. You can have registration date, you can have registration method, and all those kind of things. Any additional information that you want to track for the activity of a student enrolling for a course and a course having a particular student. Okay. So this is how you would solve, if you remember, when we were discussing the importance of good database design, I asked you if you could solve this issue, where you separate the context and then link them by the use of a new table. So this is how it is basically done. Okay. So this is how you will implement 1:2 or M:2 N. So a note after this, let's say a note on data redundancy, and this is important to remember, is that data redundancy in the DB environment, and this is specifically in the DB environment, data redundancy is not evaluated by looking at how many duplicate copies of a particular data is present. A data is said to be redundant if even after its removal, it can be recomputed using other existing attributes and relational algebra. Okay. So now if you want to accept it, so another important remark from the book itself, another important remark is you should minimize data redundancy unless you are trying to preserve the historical accuracy of data. So of course you will need additional copies, or you need to keep it for performance, let's call it database performance purposes. Okay. So for the example of the first two, we will discuss this in more detail when we get to chapter 5 and different kind of database design perspectives that we need to keep in mind. But just to give you a peek insight into what it means, is like, let's say if you're trying to generate the sales report for all the different sales that you have made in the past 5 years or so, right? So in that situation, you would like to preserve the price of a particular product rather than deleting it and keeping the most up-to-date price. Because the price that was there for the product back 5 years ago is not the same. So in order to maintain the historical accuracy or preserve, then you would want to have data redundancy. And then the other argument is when you should keep data redundancy is if you're wanting to improve the database performance, right? So for example, we said that the test of data redundancy is to see that if you remove that data value, if you can recompute it using other existing attributes and relational algebra or any other arithmetic operation, right? So for example, when you're computing the student GPA, GPA is basically a summation of 1 is to n semesters, okay, where n is the semester, and then your grade in a particular course. So basically grade as a function of course, and then different courses that you're going to take, okay? So something like this. So you will compute that and you divide it by total number of semesters, and I don't know the exact formula to compute GPA, but you get the idea. So that means that if you have a column which is student GPA, it does not have multiple copies, but it's still redundant data. And the reason behind it is because you can see the enrollment and the letter grade of a particular student that might be present in the registrar's info table, let's say. And then you can use the formula to compute the GPA to get the final grade point average, right? But if for many semesters and doing this for all students takes a lot of time in order to return the result, then it could be quite intuitive for performance purposes to retain this redundant column of student GPA, which can still be computed even if it is removed, right? So the same goes for any other data value that can be computed by using other attributes that are present as well as relational algebra, okay? So that is basically the idea. So of course we will discuss this again. We will revisit this in terms of database design when we go to chapter 5. But what I want to bring to your attention is this part here, is what is the test of data redundancy in a database environment. This one is pretty important because generally students overlook the fact that whenever they listen or whenever they're asked that, oh, is this data redundant in the database environment, their go-to answer is to check for duplicate copies of the data. In the file system environment, that is true. Okay, when we're talking about file systems, that is completely applicable, right? But if you're in the database environment, there is a more rigorous test for data redundancy, and that is to see that if you remove the data, can you generate that data back again by using the other existing attributes and taking the aid of different relational algebra operations. If you can do so, then that is redundant. Now, whether or not you should keep it or not depends on the type of design that you're trying to generate, which could be in the form of maintaining historical accuracy of data, preserving, or if you need to retain it for performance perspectives. And we will discuss this in detail later on. Okay? So the final topic are basically indexes. Okay? So indexes we will discuss in detail when we are going to go into chapter 11, which is database performance tuning and query optimizations. But just a quick peek of what indexes does is that each table can have more than one indexes, okay? But a given index will be associated with a single table, okay? What indexes helps to do is it logically rearranges all the row in the table based on the index key, okay, which is nothing but the attribute which is used, that is the attribute or set of attributes that is used to define the index. Okay. So the objective of this is that it speeds up data retrieval or data location, locating data and retrieving it, which is basically search operations. Okay. So that means if you implemented, let's say, if you have a table, let's go into the movies domain for a second. Okay. I just remembered about Christopher Nolan. That's why. So let's go to the movies domain and let's say we have a table called directors. Okay. And then let's say we have a table called movies. Okay. So here the primary key could be the director ID. Okay. And then here the primary key, let's assume, is something called movie ID. Okay. Now there is a 1:m relationship between directors and movie. Okay. Because a director can direct M movies, but a movie will be associated to a single director. Okay, so we have ensured the bidirectionality, and as a result, the driver of this particular relation is the director. So we are going to take the foreign key for movies and place it as director ID. Okay. So now, if we want to find, let's say there is a query which asks us that print all movies directed by director ID, it won't be this crude. You will have the name capability, but let's say you know the director ID. So director ID 007, okay, James Bond. So now, in a traditional format, if you don't have indexes, then what you will have to do is you will have to go to the movies table And then for all the rows that are present in the movies table, you will have to go through them row by row, and then you have to go to the column which is director ID, and then you have to check for each row that you visit whether this director ID is equivalent to 007. And if true, then you take that row, extract that row for your result set. Otherwise, you move on, right? So now that means if n is the total number of rows in your movie table and the value of n is very large, okay, so that this process of scanning this table row by row is going to take a lot of time. However, if on this movie table you create an index, and let's call it directors, and provide it the key, which is the attribute director ID, then for all the unique existence of director IDs in the movie table, it will map the movies to the director ID, right? So now, let's say even if n is very, very large, if the number of directors here in this director table is, let's say, m is equals to, let's say, 10. So the moment you create this index, the database will by itself take 001 and then associate to it or logically rearrange the rows in a certain way that all the movies, let's say 111, 112, 113, and then 002, it will take, let's say, 333, 44, 56, and 52, and so on. And then for 007, it will do the same thing. Okay, that is, it will associate all the rows that is associated to the index key 007. Okay, so now if you again run the same query, then the database is going to see that, hey, there is a index name called directors, which uses the director ID as the index key, and there is a key mapping, key value pair mapping for them, right? So it's going to go through that index and it's going to find 007, and in a constant operation, it's going to find all the movies that are associated to 007 rather than having to go through the entire table row by row. So you see that that is the reason why we are saying that we will discuss DB indexes in more detail when we go to query optimization, because this is a process of improving the performance of the query execution. Okay, and as you can simply see that it will take basically 7 steps to get to 007, and then if you remember hash maps or hash tables, it's going to take a single step in order to retrieve all the rows. Okay, so that is the performance of DB indexes. Now along these lines, there are different types of indexes, right? One, you can create a unique index. So unique index is nothing but, as you saw here, these are non-unique indexes because each index key is mapped to multiple rows, right? But if you create an index on primary key, well, you don't have to create an index on primary key because the database, the moment you declare an attribute as primary key, is going to create an associated index for it. So unique index is basically an index key that has only one mapping, only one record mapping, okay, or basically a single pointer location or a single reference. Then that is basically a unique index. So anything that is not unique is basically a non-unique index. And the example that we saw here is basically that of a non-unique index. So that basically concludes part 2. Part 2 and chapter 3, which is the relational model. So the key takeaways that you have to look out for and study, combining both part 1 and part 2, is of course the first one from part 1, the important part, is functional dependency plus the concept of keys. Okay. And then you have the relational operators and relational algebra. So we will do a few examples of this when we get to SQL. So we will try to write the relational algebra form, and then we will try to write the SQL form. It will be fun. And then the note on data redundancy. This is very important. This is very, very important. Okay. And then the implementation of relationship types using keys. Okay. So in addition to that, we had this index thing, but again, we will revisit it. But on an introductory level, you kind of get the idea from this particular example that what indexes are there for or how you can use them. Okay. So that concludes chapter 3. Okay. So in the next lecture videos, we will be discussing about how to further simplify the graphical representation of our database design. And for that, we will basically cover the components of the entity relationship model. Okay. So I will see you all again in the next lecture video. Until then, stay safe and take care.